RISC architecture is going to change everything.
The movie Hackers is probably not the most popular or well-remembered hacker film, but that quote by Angelina Jolie takes the spot as the most insanely accurate movie prediction of the century. For decades, computer companies fought this philosophical war between two fronts, CISC and RISC.
RISC is good.
I'll get to what that means in a moment, but this is a war that for the average person went completely unnoticed, but that has transformed your computer in more ways than you can ever imagine. It's a war that allowed a tiny UK startup that doesn't even have the capacity to manufacture chips to become one of the most valuable companies in the world and to turn a giant like Intel into an almost irrelevant company for today's computer. And to understand how this happened, we need to open the hood inside the hood of your computer and look into the invisible company that powers the world. Now the story is gonna be in this chart. This is the number of transistors that we can fit inside a processor, but there's a dangerous hard limit to this. But first, let me show you what it means. If a processor is a computer's brain, then each transistor is a neuron. And this thing is easily the most crucial invention of the 21st century. It's the backbone of everything from a calculator to your car computer to the server that runs your chatbot.
How would you describe your relationship with your mother?
For years, our brightest minds, our scientists, have shrunk transistors to the size of a few atoms. But what we really discovered is that size isn't everything.
What does matter is the size of your heart and the strength of your character.
And what better way to explain this than with Minecraft blocks? So I've been working on this little contraption here, which is two cables connected to these levers, to this thing here, I'll explain it in a sec, and then to this output going out to this lamp. So the idea here is that you need both of these levers to be on, sending current through these cables so that this output cable still works. If one of the levers is off, then the contraption doesn't work. This is called a logic gate. In this case, an AND gate, which again requires both of these to be on for the contraption to work. And this is the backbone of pretty much every computer in the world today. Like your device where you're watching this, your TV, your phone, whatever, has billions of these things inside. That's in essence what this little thing does. It's a semiconductor. It transmits electricity only if certain rules are met. But when you combine enough of these, you can build anything.
This is a fully working calculator in Minecraft, complete with addition, subtraction, multiplication, and division.
The transistor earned its inventors a Nobel Prize. And a few years later, one of them, William Shockley, moved to this very spot in Mountain View, California, to start a company around his invention, planting the seeds for what would become Silicon Valley. In this other spot, Intel would design the Intel 4004, which was officially the first commercially available processor, and the very first one by Intel in that chart I showed you, with a whopping 2,300 transistors inside, all in this little black thing. Well, they didn't have one here at the Computer History Museum, which kind of sucks, but okay. Around that time, one of Intel's co-founders also theorized that with tech advancements, every couple of years, they'd be able to double the number of transistors that we could fit inside a single processor.
22 nanometer,
14 nanometer,
10 nanometer,
7 nanometer,
5 nanometer.
Over the next 50 years, Intel and its competitors have been able to double the number of transistors every 2 years. This chart is actually exponential. We're just using a logarithmic scale to make it easier to read. And we've gotten so good at making transistors that we can now make each one of them just about 30 nanometers wide. That means you can fit about 2,500 transistors in the width of a human hair. Now, the reason why there's a ceiling in this chart is because at this size, the transistor is so small that electrons may leak to the other side of the semiconductor. It's actually called quantum tunneling, and it's the biggest challenge and probably the physical limit to chip sizes and how many transistors will be ever able to fit inside a processor. But again, size isn't everything.
Okay.
Now the trick is in getting those billions of transistors to work together. How do you get them to do, well, anything efficiently? Not billions, but if you need dozens of people to follow the same set of instructions, you should give Notion a try, which happens to be our sponsor for today's video. Now, I write these scripts in Notion, and I create this repository of references, guidelines, instructions, processes, and tools that our production team needs. And when we onboard new people to the team, Notion lets them hit the ground running with the tools and the processes that they need. It's hard to explain a little bit how Notion is so useful, but to me the answer is just on the user experience. Because every function is just a keyword shortcut away, and it mixes features from a text editor, from a blog platform, from a website builder, and from even like a full-on database. And more recently, they upgraded it with the new Notion AI functionality with a brand new user interface where actions are just a click away instead of having to write a prompt away. And it also features a chat function that's connected to models like Claude and GPT-4. Now, while scripts are still a very personal thing, and I tend to avoid using any generative AI for these, I do use those features for pretty much everything else. Notion is our dev team's repository for instructions and website, database structure, and how things work in the back end. It lets any new engineers understand our tech stack. Our entire office guide is on Notion with clear instructions what to do, who to call if the internet breaks, and the step-by-step guide for when, say, you're the first one in or the last to leave. We also use Notion to create and share quotes with clients. We have this template that we reuse. We link it to existing resources. We have a glossary of how the process works and share them with our leads as published web pages that automatically get disabled after a week. You can also connect Notion AI to Slack or to Google Drive, and you can literally task this tool with hunting for deadlines or your key messages or project updates from your company's document repository. Now, the team at Notion created this unique link that you guys can use to get free access to their platform and unlock the new Notion AI. And if you use the link, you're also supporting our channel and our videos in the process. Thanks a lot, Notion, for helping us make today's video. Now, making processors work is not just about shrinking transistors, but also about letting people build software that uses those chips. Now, when you code, you generally use what's called a high-level programming language, maybe JavaScript or Swift. They're relatively easy to read and to understand for us humans, but it's not the language that your computer processor speaks. That high-level code that you write needs to be compiled into instructions that your computer can understand. Intel created the instruction set that most processors would use through the beginning of the 2000s. It was called x86, and that is the very first chip built with that architecture. So let's say that we want to add one subscriber to our YouTube channel. Maybe it's you. You can try the button, see if it works. Now, if you did press the button, what the system needs to do is retrieve the number of subscribers that our channel already has and add one. Now, much of YouTube is written in Python, but that's just a high-level language that Google's developers used. Now, I'm gonna oversimplify a few things, but in essence, when a high-level language gets compiled, what actually happens is that this language gets translated into instructions that a CPU, the processor in your computer, can understand. In this case, x86 CPU instructions. And in x86, the code that you need for adding a subscriber ultimately looks something like this. In plain English, that means inc, increased, the value in a register, in this case, our subscribers, by 1. Now that's a single instruction. One line, one instruction to do this set of actions. You don't need to write anything else. The inc instruction already implies that you're adding one, it takes care of everything else. Now that is the backbone of Intel's thesis. Single advanced instructions that can do many things at once. That's called a CISC, a complex instruction set computer. But adding one subscriber for a processor is not that simple. The addition, just adding, 597,000 plus 1, will ultimately be done by those Minecraft transistors that we built earlier. And in a processor, all those transistors are bundled together in an area of the chip that we call the ALU. But we need to translate this operation for them. Inc is not something that those transistors can do. Inc is too complex of an instruction. It actually needs to be broken down even further. For example, fetching how many subscribers we currently have, adding 1 to that number, and then storing the new value. Again, the inc instruction summarizes all of these actions, takes care of all these subtasks for us. But someone needs to break down to translate inc into these smaller instructions that the ALU can execute. They're actually called micro operations, micro-ops. Now that someone is the processor's control unit, which then schedules those micro operations for the ALU to perform. Now this design was sound. Pretty much every computer in the 90s was built on top of this architecture, and Intel based its entire empire on x86. And so did AMD, by the way. They licensed x86 from Intel and built processors using the same architecture. And with time, Intel has written nearly 1,000 possible instructions for this x86 architecture to handle everything that a computer might do. However, 1,000 instructions also meant that the control units in their processors got more and more complex with time. And that wasn't much of a problem for the developers. It was Intel's problem to solve, and for the most part, Intel managed to solve it. It was all dandy for Intel as we approached the 2000s and the movie Hackers.
RISC architecture is going to change everything.
Now, RISC is CISC's sworn enemy. It stands for Reduced Instruction Set Architecture. Now, the first commercial chip with this architecture was the IBM 801, developed at IBM's New York Research Center. The philosophy of RISCers, which is a thing that I totally made up for this video,
What is RISCers?
Oh, it's like slang. Oh, English.
was that you didn't really need this complex long list of instructions instructions on your processor. Instead, you could just have a simpler list and then make the compiler do more work in simplifying your high-level code so that the CPU can handle it. Now let's say that, again, we want to add another subscriber. Maybe you didn't take the first chance to subscribe and try this feature out. Like before, the ALU, that part of the processor, can add the subscriber. They can't execute Python, so the compiler converts that to CPU instructions. But in a RISC system, the compiler can't use ink. That instruction doesn't exist. Instead, it has to write out 3 separate instructions. First, load, LDR, the current subscriber number. Second, add, and then you have to actually write the one that you want to add. And then store the new value. So the compiler had to be much more detailed, break down Python into every primitive instruction that the ALU can execute. The significant advantage of this, though, is that the control unit ends up being much smaller, simpler. Each instruction maps to a simple control signal that the ALU understands. And the overall chip design is simpler and just more efficient. And this was, for many sorts and purposes, better than CISC. It was potentially faster, definitely more power efficient, but who cares about that? IBM bet many of its chips on a RISC architecture, and so did Sun Microsystems. Companies like Acorn as well, they built entire workstations on top of RISC architectures. This one, for example, the Acorn RISC machine, or ARM. Now, they might have been good at naming and making efficient chips, but Acorn, they weren't that great at selling computers. In the 90s, with some help from Apple, they turned away from building computers, and they just started focusing on designing RISC chips. And they became a company called ARM Holdings, which will be really important in just a moment. And the point is, Apple really believed in the RISC architecture too. Most Macs I grew up seeing in the 90s were based on the PowerPC chips, which used the RISC instruction set that Apple, IBM, and Motorola designed, called IAM. It's one of the reasons why Windows software was just terribly incompatible with Macs back in the day. The 90s weren't kind to RISC companies because Windows was absolutely killing it. Now, PC obliterated the computer market in the 90s. Windows became the world's operating system, and so all popular software ended up being built for an x86 architecture. It didn't matter that RISC processors could be better or faster, because nobody wanted to port software. Porting software wasn't just building your software for another operating system, it was for a completely different type of computer. Intel was a monster, keeping up with Moore's law, packing more transistors, making faster processors, and no RISC-focused company was realistically gonna catch up with them. Now, the complexity of x86 instructions came with challenges, but Intel overcame these challenges by essentially loading up their Pentium processor series with features to counter those CISC pitfalls. The processors became more complex, a bit less power efficient, but in the end, faster, and everyone was happy. The annoyance of porting software and not having any major RISC chip manufacturer nearly killed RISCers in the early 2000s.
That was so
RISCers.
By 2010, 90% of new data center Linux deployments ran on x86. Apple ditched its PowerPC and started putting Intel chips in its own computers. Early 2000s, ARM, the Acorn-Apple joint venture, was one of the only RISC companies that was doing decently well. They went public in '98, and they were still designing chips for little, mostly insignificant devices, what geeks would call embedded devices, your calculators, your Palm, remember those? And those rudimentary phones from the early 2000s. No Intel chip for those. Intel chips were performance, power hungry, with that monster of an architecture, but you know where this is going.
An iPod, a phone. Are you getting it?
Now, ARM chips were just not ready for the computer leagues at this time. But Apple did call in their side hustle to design the chip that they would eventually put on their first iPhone. The first iPhone had an S5L 8900 system on a chip that was manufactured by Samsung, but used ARM's RISC instructions for their CPU core. This new product category, smartphones, well, they're like small mobile computers. They put ARM chip designs to the test, and call it what you want, but the iPhone's success made RISC chips relevant again. ARM architecture became the absolute standard for mobile. And this was new hardware, a whole new platform, a new type of screen. Old software had to be rebuilt from scratch anyway, so everybody just kind of went along with having to make new stuff that worked on top of this new RISC system. Samsung released the Galaxy in 2009, also using an ARM CPU, and so did major phone manufacturers in the years to come. And when the iPad came out in 2010, these ARM chips started to transition, to start do things that a desktop computer would do. And meanwhile, Apple's romance with Intel, it was starting to run into trouble because in a desktop computer, power use and temperature, that's not that relevant, right? You just add more fans. But in a laptop, which is a mobile device in the end, there's only so much battery life that you can squeeze out of an Intel chip. Fans make noise and they draw a lot of battery, and there was only so much that you could do if your processor was an Intel chip. And here comes the breakup. In November 2020, Apple finally divorced Intel and started transitioning to its current ARM-based M1 or M4 processor series. Whole new architecture, new software that we have to build again? Not really. Thanks to a decade of iOS and Android apps, we now have this massive library of software that doesn't need to be ported again. It was already built not just for RISC, but for an ARM architecture. It was software built for efficiency with performance and battery life in mind. And other companies followed suit. Disclaimer, by the way, Apple wasn't the first company to try to put ARM chips on a laptop, but smaller companies and their netbooks weren't really gonna get the world to shift back to RISC. Estimates say that by 2029, 40% of laptops in the world will be based on ARM chips. But it's not just the laptops, of course. Apple has put the same ARM chips on desktop computers as well, and they're killing it in performance. They've proven that ARM can seriously outperform Intel's x86 for even desktop applications. So in other words, Apple has given RISCers a comeback for the ages.
Stop trying to make
RISCers
happen. It's not going to happen.
ARM-based cores have now been added to over 280 billion devices as of last year, mostly mobile, but slowly creeping its way into server applications too. Amazon Graviton instances, which are ARM-based now, they power 20% of AWS's workload. Even NVIDIA is adopting ARM designs in its Grace CPUs. x86 processors still have a slight advantage for large server applications, but that edge is shrinking pretty quickly. And that is why Intel is in absolute panic. Very late, they've started to invest back into some RISC initiatives, but beginning to compete requires them to essentially rewire everything that they've stood up for decades. And it just may be too late. And here's the wildest part. ARM, the company, doesn't manufacture chips. They just license the idea for chips, their architecture. It's like winning Formula One without even having to build a car. Today, ARM's design powers your iPhone, your laptop maybe, your smartwatch, your fridge, maybe even the servers where this video is streaming from. NVIDIA tried to snatch the company for $40 billion, and it was honestly, thankfully, blocked. Because can you imagine the monopoly of NVIDIA owning ARM? As for Intel, I mean, they still power your uncle's old Dell desktop, and the RISCers are getting the last laugh. ARM is quietly pulling in billions of dollars. They're redefining modern computing. They don't have to worry about tariffs or anything because they don't make chips. They're doing it all behind the scenes without anybody knowing. And so now that you understand this war, who's winning it, you understand the chart and the philosophy, would you still bet on Intel to recover? I mean, it sounds like we should have been listening to Angelina Jolie all along. She was right. By the way, if you enjoyed this video, you should watch our video on the AI paradox and why there's a limit to how smart our AI can be. We'll catch you in the next one.